In this video clip, I'll tell you about the self-organizing map, or someone say that this is self-organizing feature map, or SOM. You can you can think that this is self-organizing map, or someone say this is a feature map, self-organizing map, or self-organizing feature map. This is another method that we can use to to cluster the data. How different from the k-means? The As you can see, the disadvantages of or the drawback of the k-means is we have to define k, but for SOM it's different. The idea of SOM is we have two layers. The first one is we call the coordinate layer, or you can think that this is like a plane, some plane like this, that you have the set of nodes that it will be organized and has the the structure that for example, this is if you think that this is node 1 2 3 4 5 6 7 8 9 10 11 12 13, 14, 15. Node number one is connection, has the connection to node 2 and 5. We call it the neighbor. So neighbor of 1 is a set of 2 and 5. Okay. Neighbor of node 7 is 3, 6, 8, and 11. Oh, sorry, I draw the. Okay. So this is the neighborhood one. So the idea is different from the k-means, but it's like almost same. For example, if you have two inputs, or the dimension of your inputs is 2, we have x1 and x2. Same thing as you have x and y, and you declare this one, this is x1 and this is x2. For example, we have two dimensions, that is x1 and x2. For this is another layer, we call this one the coordinate layer. The idea of coordinate layer and the input layer, this one is the input layer. Yes, from input layer, you have connection to each node. For example, this is x1 and x2 that connect to node number 13. And for x1 and x2 that connect to 13, you have some weight, like 2.1 and 3.8, for example. And we must have this kind of node, this kind of connection to all nodes in the coordinate layer. So we must connect. So this will be very like very complicated, and it's not so nice to draw all of them. But you can see that, for example, we have a node number 13, and we have 2.1 and 3.8 that connects to x1 and x2. So this is the input layer to coordinate layer, and we have this kind of nodes to all nodes in coordinate layer, to node number 1, right? And we have x1 and x2, x1 and x2, x1 and x2 to node number 16. So our x1 and x2, our link here, all of them must have the link and must have its own weights that connect to the nodes in the coordinate layer. You can think that this one, the weight of x1 and x2, you can represent it in the space like this. This is x1 and x2. This is the dimension. X1 is on x-axis and x2 is on y-axis. Uh, x1 is 2.1, x2 is 3.8. So you can represent node 13 here. Okay, so all of the nodes in the coordinate layer, it must have the its own location. For example, 12, 11, 10, 9, 8, 7, 6, and you must have all of them, all 16 nodes. And it must have the connection, right? From 13 to 14 here, 13 to 14, for example, if this is node, if node 14. So you must have a connection between 13 and 14, this one, and 13 to 9, right? So you must have the connection to from these nodes, right? Right? And you must have 11, 10 to 11, 10 to 9, 10 to 6. For example, this is 10 to, oh, sorry, we already had 6 here, and 10 to 6, and 10 to 11, 10 to 9, and 10 to 14. So you must have the link here. So this one is like the connection between the neighbor. So the idea is, once you have the data in the same space, of course, data has its own coordinate, right? For example, this one can be like 3.8 and 0.9, for example. So this one, there's example 1 that is in location 3.8 and 0.9. The idea of SOM is quite simple. Look at this. You must find the winner node. You must find the winner node of the coordinate layer. Winner node in coordinate layer. That is the node that has the weight that is closest to this example. For example, this one. Uh, this is the closest node, right? This is the closest node, right? For example, if this is the node number 2, if this is the node number 2, the winner node is node number 2, and the node number 2 is connect to 1, 3, and 6. So node number 2 has the, I will draw it using the red one. Node number 2 connect to node number 1. We don't have node number 1 yet, right? So I will draw it. For example, this is node number 1. So this is the connection of the neighbor to the winner node. 2 connect to 1 and 2 connect to 3 and 6. 2 will connect to 6 and 2 must connect to 3. We don't have 3 yet, so I will draw it somewhere, for example. So this is the node number 3 that node number 2 connect to this one. And guys, the idea is quite simple. For the nodes, whose winner node, it must be moved closer to this example, and same as the all of its neighbor. So it must move to, the direction is move to x. Okay, so this one will move to x also. So the node will, the winner node and its neighbor will move to next this example. So in the next iteration, node number 3 will be moved here. Node number 1 will be moved here, and node number 6 is moved here. Okay, node number 2 move here also. So you can see that for these steps, this step will, it is like moving the winner node to this example. So once we represent all, when we present the example, each example to this structure. For each example, for example, if we have x, another x like this, we must have the winner node around here, right? So for example, if node 9 is the winner node, we must move 9 to this, and its neighbor. So 9 connect to 10, 5, and 13. So 10 must be moved to here also. And 5 and 13 must move. So, right, 9 will be moved here, and 5 also. So you can see that for this kind of structure, it is quite like simple. And we will try to understand this algorithm through the programming. Okay, very simple one. So please take a look at our source code for SOM. See you in Colab.